Well done for completing the first 5 sections. In this section we move on from looking at the principles and instead look at the first of the load groups that we will use, which is resistors. The aims of the course today are: show the difference between series and parallel resistor circuit, provide methodology on how to add together resistors in different configurations, see how we can use resistors to change the output voltage, here is a circuit containing some resistors all connected in series. So we have 3 resistors, RA, RB and RC, connected in series to a live and neutral terminals. The first thing to note is that in a series circuit, the current is the same in all resistors and flows through them equally. Let's now look at the voltage across each resistor. From Ohm's law, voltage equals current times by resistance. Therefore, the voltage across resistor A, VA, equals I times RA. Let's now apply that to all the resistors shown above. So we have voltage A across RA, voltage B across RB, and voltage C across RC. And what about the input voltage? Well, that's just a summation of the 3 series voltages. Therefore, V total equals VA plus VB plus VC. Let's now add some series resistances together. Here's the chain from before with the resistors RA, RB and RC all connected in series. A series resistor chain can be represented by a single equivalent resistor. In this case, the resistor is R total. For the equivalent resistor value in a series circuit, simply add the resistance values together. R total equals RA plus RB plus RC. Here is a worked example. Here we have a series chain of resistors with values of 20 ohms, 35 ohms and 80 ohms. What is the equivalent resistor value? From the previous slide, R total equals 20 ohms plus 35 ohms plus 80 ohms. Therefore, R total equals 135 ohms. Note that the equivalent resistor value is larger than any of the individual series resistor values. We can also use a series resistor chain to change the output voltage. This arrangement is called a voltage divider. The value of the output voltage Vout is decided by the ratio of resistors A and B. The output voltage Vout equals the input voltage times by RB divided by RA plus RB. Here is another worked example. Here we have the voltage divider chain from the previous slide. This time RA is 22 ohms and RB is 88 ohms. The question is, what is the output voltage where the resistance is shown? The output voltage Vout equals the input voltage times by RB divided by RA plus RB. Therefore, the output voltage Vout equals 230 volts times by 88 ohms divided by 22 ohms plus 88 ohms. Therefore, Vout is 184 volts. Let's now look at a circuit containing some resistors, all connected in parallel. Here we have resistor RA connected to a live and neutral. In parallel, we have resistor RB and resistor RC. Let's look at the voltages. Firstly, we have the input voltage Vin, VA, the voltage across RA, VB, the voltage across RB, and VC, the voltage across RC. In a parallel circuit, all the voltages are the same. Therefore, the input voltage equals VA equals VB equals VC. What about the currents? We have current IA flowing through RA, current IB flowing through RB, and current IC flowing through RC. From Ohm's law, current equals voltage divided by resistance. Therefore, IA equals the input voltage divided by the value of RA. IB is the input voltage divided by the value of RB, and IC is the input voltage divided by the value of RC. And the total current drawn from the system? The total is simply the sum of all the individual currents. Therefore, I total equals IA plus IB plus IC. Let's now add some parallel resistors together. Here we have the previous circuit with RA, RB and RC. This chain can be represented by a single equivalent resistor, R total, where 1 over R total equals 1 over RA plus 1 over RB plus 1 over RC. Let's do a worked example. Here's the resistor chain from previously with RA, RB and RC. What is the equivalent resistor value? Well, 1 over R total equals 1 over 20 ohms, which is RA, plus 1 over 40 ohms, which is RB, plus 1 over 50 ohms, which is RC. Therefore, 1 over R total equals 0.05 ohms plus 0.025 ohms plus 0.02 ohms equals 0.095 ohms. Therefore, inverting the equation, R total equals 1 over 0.05 ohms is 10.52 ohms. Note that the equivalent resistor value is smaller than any of the individual parallel resistor values. Let's now look at how a resistive load affects the current and voltage waveforms in an AC system. Here we have the standard amplitude time graph we've seen before. Let's add the voltage sine wave. And next the current sine wave. Let's compare the two. The phase angle is the angular difference between the voltage and current waveforms. In a circuit containing a purely resistive load, the current and voltage waveforms are in phase. The phase angle phi is therefore 0. The power factor is cos phi, that's 1. We can also show the relationship between the current and voltage waveforms using a phasor diagram, as we've done previously. In this case, the voltage, let's make it a horizontal line as a reference point. Let's add the current. Again, a horizontal line. As the current and voltage waveforms are in phase, the phase angle is 0, they both point in the same direction. Let's look again at the power equation. power is voltage times by the current times by the power factor. In a resistive load, the power factor is 1. Therefore, the power is the voltage times by the current. The power factor has no effect in a resistive circuit. Let's summarise what we've learned today. When resistances are connected in series, the current is the same through them all. The voltage is different across each resistor depending on its value. When resistances are connected in parallel, the voltage is the same across them all. The current is different in each resistor depending on its value. And finally, in a purely resistive AC circuit, the power factor is 1. Congratulations for making it through 6 sections. I've attached some test questions in the course content. Please try them before going on to the next section, which will introduce capacitors. These are the second of the 3 load groups that we use.